Greetings, everyone. My name is CHRISTMA with matrix number CD240063. I will be presenting our work on the passive cooling simulation. As semiconductor logic density skyrockets, managing heat flux has become one of the most critical challenges in engineering design. Maintaining junction temperatures below 85 degrees Celsius is no longer just a design goal, but it is a non-negotiable industrial requirement. If we fail here, we risk hardware failure and system throttling. Our objective is to design a robust, passive solution that offers the reliability and silent operation of a fanless system while meeting the performance demands of modern high-performance electronics. Our project operates within a strict 60 x 60 mm footprint constraint. To achieve our cooling goals, we are using two-fold methodology. First, we are establishing an analytical baseline by calculating conductive and convective thermal resistance for aluminum 6061. However, analytical models often oversimplify. That is why we are pairing this with numerical validation using SolidWorks simulation. This allows us to map real-world temperature distribution and airflow paths, moving far beyond theoretical limits into high-fidelity modeling. As noted in our literature review, the core design challenge is the optimum fin spacing trade-off identified by Bar-Cohen and Liengar. If we increase fin density, we increase surface area, but we also increase fluid drag and boundary layer interference. Our parametric analysis focuses on finding that sweet spot. We aren't just looking for maximum cooling, we are looking for the optimal balance between surface area augmentation and minimizing fluid flow impedance. By combining analytical rigor with modern CFD validations, we are developing a design that ensures high performance reliability under industrial conditions. This project demonstrates our ability to take a complex thermal management problem and engineer a durable zero energy solutions. Thank you.
Hi, good day everyone. My name is Sean PRAVEEN and my matrix number is CD240207. So today we are reviewing the results of our thermal optimization study for our 10-watt silicon chip using aluminum 6061 heatsink. So as you can see on the left of the dashboard, our phase 2 simulation focused on the baseline case. So we used SolidWorks flow simulation to map the natural convection cell. The key finding here was the chimney effect. A trap between the fins absorbs heat, loses density, and creates a buoyancy-driven plumb. While our base case performed at 77.73 degrees Celsius, our goal was to push this thermal threshold even lower. So now let's move to phase 3, where we tested 4 design iterations. The most critical lesson came from iteration 1. So in an attempt to increase surface area, we increased the fin count to 15. Counterintuitively, this was a disaster. The temperature skyrocketed to 102.42 degrees Celsius. This is a classic case of thermal choking, where the air gaps were so narrow that the buoyant draft couldn't penetrate the core, leading to a massive heat stagnation. So we also tested a pin square matrix in iteration 4. While this provided excellent omnidirectional flow and reduced the weight to 132 grams, the dense packing will still create too much resistance compared to our longitudinal designs. So the clear winner here was iteration 3. So instead of adding more fins or changing the type, we maintained the 10 fin count to keep the airflow channels open, but we extended the vertical height to 45 millimeters. So this structural strategy maximized the heat transfer surface area through vertical extension without increasing flow resistance. The result was our lowest stable operating temperature of 69.03 degrees Celsius, so nearly 9 degrees cooler than our base case. In summary, the study proves that in natural convection, geometry and airflow pathways matter more than the raw surface area. By optimizing the vertical conductive path and ensuring unobstructed buoyancy, iteration 3 provides the most efficient thermal management solution for the stand workload. Thank you.
Hello, my name is Cassandra KAJAN. My metric number is 230 DD2300027, and now I will present for our result. This slide show this slide show the temperature distribution of the best case heat sink obtained from SolidWorks flow simulation. The highest temperature is concentrated in the chip surface where heat is generated. Heat is then conducted through the aluminum heat sink and dissipated through the fin through natural convection. The temperature gradually decreases from the heat source toward the fin tip, indicating effective heat transfer throughout the heat sink structure. The maximum chip temperature recorded was 77.73 degrees Celsius, which is below the allowable operating limit of 85 degrees Celsius. Therefore, the best case design is capable of maintaining safe operating conditions for the microprocessor. This slide presents the airflow behavior around the heatsink using the velocity cut plot and flow trajectories. The simulation showed that natural convection occurs around the heatsink as heated air become less dense and rise upward due to buoyancy effects. At the same time, cooler ambient air enter the fin channel to replace the heated air. The flow trajectories confirm a continuous and stable airflow circulation pattern around the heatsink. This airflow mechanism enhance convective heat transfer and help remove heat effectively from the heat surface, improving the overall cooling performance. This slide compares the thermal performance of the best case and all design iterations. The best case achieved a maximum chip temperature of 77.73 degrees Celsius. Iteration 1 recorded the highest temperature of 102.1.42 degrees Celsius because the increased number of fin restricted airflow between adjacent channel, reducing the effectiveness of natural convection. Iteration 2 and Iteration 4 improved the thermal performance, achieving maximum temperature of 73.29 degrees Celsius and 73.14 degrees Celsius, respectively. Among all configuration, iteration 3 achieved the lowest maximum chip temperature of 69.03 degrees Celsius. This improvement was achieved by increasing the fin height, which provided a large heat transfer surface area and enhanced heat dissipation. Therefore, iteration 3 was selected as the optimum heat sink because it provides the best cooling performance among all configurations evaluated in this study.
Greetings everyone, my name is Samuel Gawe Ananaun and my matrix number is CD2400087. Today, I am presenting the findings of our heatsink parametric study, which we conducted to optimize the passive cooling performance of a microprocessor under natural convection. Our primary mission was clear, which is identify a design that comfortably keeps the maximum keep temperature below the critical operating limit of 85 degrees Celsius. We began with a base case rectangular design, which achieved a safe maximum temperature of 77.73 degrees Celsius. This served as our benchmark. To improve on this, our iteration increased the fin count to 15 to maximize surface area. However, iteration 1 fell catastrophically, peaking at 102.42 degrees Celsius. This highlighted a vital engineering lesson, which is simply adding surface area is counterproductive if high fin density chokes airflow and stalls buoyancy-driven convection. We corrected this in iteration 2 by reducing fin thickness to 1 millimeter. This opened up the air channel, facilitated better ambient air intake, and actually and successfully dropped the temperature by over 4 degrees compared to the best case, bringing it to 73.29 degrees Celsius. Our best performing design was iteration 3. By increasing the fin height to 45 millimeters while keeping open spacing, we triggered a powerful chimney effect. This accelerated the buoyancy-driven airflow, achieving our absolute lowest temperature of 69.03 degrees Celsius, an impressive 8.7 degree drop of our baseline. We also evaluated a multi-directional pin fin design in iteration 4, which performed well at 73.14 degrees Celsius. But its dense layout introduced too much flow resistance to outperform the tall, open vertical channels of iteration 3. Finally, we validated our SolidWorks flow simulations against analytical heat transfer equations. This yielded a percentage error of 26.1%, which is highly acceptable given the simplified boundary assumption of the mathematical model. Thank you.
In conclusion, this study successfully evaluated the thermal performance of different heatsink configurations under natural convection conditions using SolidWorks flow simulation. The result demonstrated that fin geometry and dimension significantly affect heat dissipation performance. Among all configurations, iteration 3 achieved the lowest maximum chip temperature of 69.03 degrees Celsius. Due to its increased fin height and larger heat transfer surface area, therefore iteration 3 was selected as the optimum heat sink design because it provides superior thermal performance while maintaining safe operating conditions for microprocessor.